Guys, welcome once more to our YouTube channel. For those of you who are taking physics on Thursday GCE 2023 session, wish you all the best. BU go rocket. So let's have a quick look at Northwest Mock 2021 as part of your revision process. Okay, let's go. Ooh, this is an interesting question, guys. Again, it's waves. The examiners love waves. So pause the video, check it out. If you can solve it, that's good. Now let's go. Lights of the same color from two identical touches are focused on the vertical wall, so they overlap. State and explain whether or not a visible interference pattern will be produced in the region of overlap. Please, you tell the examiner first. Not possible. They will not cause an interference pattern as they are only monochromatic. That is if you are even using, okay, they have said the same color. All right, so they are monochromatic there. So if the examiner did not tell you the same color, then you don't know whether they are monochromatic or not, okay, which is more reason why they will not form interference pattern. But he said the same color, so they are monochromatic. But now they are from different sources, okay? They will not maintain a constant phase difference with each other. And that's why you notice that for interference pattern, for interference experiments, you get a laser beam or a light source, you shine it through a single slit first before it goes to the double slit. The single slit is making sure that, hey, we can give the waves a similar phase relationship, and then when they now go ahead and interact on the two slits, yeah, we can have a constant phase difference between these waves. All right, so we're using one source of light there, but here you're using two sources of light. They don't maintain a constant phase difference with each other, okay? And that is a vital point for the formation of an interference pattern. Hey, the waves must be monochromatic, like they've said here. They must maintain a constant phase difference with one another, okay? They must have comparable wavelengths or amplitudes, all right? Comparable amplitudes. Okay, so let's go. In a Young's double slit experiment, light of wavelength that was used to illuminate the double slits, the slit separation is this, and the distance from the double slit to the screen is this. So that's a slit screen distance. Through what distance would the center of the fringe system shift if a thin sheet of transparent material of refractive index 2.4 and thickness 3 micrometers is placed over one of the slits? Very interesting. Now, our general interference equation is lambda equals AX on D, okay? A there is slit separation, X is fringe separation, D is the slit screen distance, all right? So we can make X the subject, which is our fringe separation. Let's look for the fringe separation in this particular interference experiment with these on parameters. So our lambda there is 5 times 10 to the negative 7. That's the wavelength of the light. Our X there, okay, our D there, sorry, which is the slit screen distance, 80 centimeters, put that in meters as 0.8 meters. Our A there is a slit separation, which is 0.4 millimeters. Of course, that's 0.4 times 10 to the negative 3. So notice that our fringe separation for this normal interference pattern without you putting the transparent material is 1 millimeter. That's our fringe separation. But now, what happens when you put the transparent material? When the transparent material is in place, now there's an extra part difference between the waves that are from the slit without the transparent material, right, relative to the waves that are from the slit with the transparent material. And that's how I calculate the path difference, okay? The point where they're interacting now to form a bright fringe, okay? So how far would the center, because hey, through what distance would the center of the fringe system shift? So I just want to calculate how far that center bright fringe would move, okay? Because the center bright fringe is formed when the path difference between the waves is equal to m lambda, okay, whole number multiple of wavelength. So you realize that the path difference there will be n minus 1 times t, where n now is the refractive index of the glass in place multiplied, see here is the thickness, all right? So you realize that, hey, our m there, which is through what number of integer values of lambda would that thing move? So let's look for m now. So we are going to make m subject, of course, n minus 1 times t divided by lambda, right? So n is 2.4 minus 1 times t. Our thickness there is 3 micrometers, so you put that there. So our m is 8, okay? So you realize that the extra part difference shifts the center bright fringe through to the 8th bright fringe. This is what this really means. The distance the center of the fringe system moves is therefore mx, okay? Because the center bright fringe now has moved from zeroth order to the 8th bright fringe, okay? So you realize that our distance now would basically be 8 times the distance, this is a particular fringe separation, all right, which is basically 1 millimeter we calculated from above here. So that's 8 distance that the the fringe system would move is 8 millimeters. This is a very, very interesting question. Guys, let me know if you understood it. Let me know if you enjoyed it. Let me know if there are any worries you have about it down in the comment section below. Or if you paused the video and solved it and got it right, also let me know in the comment section below. I would love to see that. Thank you guys so much for watching our content.